Hello guys, let's talk about nuclear stability. So if we have an atom that has more than one protons, it is going to have repulsions between the protons in the nucleus. And nuclear stability helps us identify the stability of an isotope using two main factors. The first one is the neutron-to-proton ratio, and the second one is the total number of nucleons in the nucleus. So when I think about neutrons, I think about them as stuffing between the positively charged protons, as neutrons have no charge. So it kind of makes sense that up to a certain point, it's enough to have a neutron-to-proton ratio as 1:1, and when we have higher number of protons, we are going to need a larger number of neutrons as stuffing to keep the nucleus together. So for smaller nuclei, so below atomic number 20, we are going to have stable nuclei, have a proton to neutron ratio as 1:1. And nuclei that are larger, they are going to stabilize by having more neutrons in the nucleus. And this is also shown in the figure right here. So we have the number of protons on the x-axis, the number of neutrons on the y-axis. As you can see that up to the number of protons of 20, we are going to have the stable nuclei, the blue dots, which is also called the belt of stability, in a ratio of 1:1, which is also shown with this red line right here. And as we increase the number of protons, this red line will be below this belt of stability, below these blue dots, meaning that we are going to have a larger neutron to proton ratio. Now, interestingly, we are going to have nuclei, and those are the yellow ones above and below the belt of stability, and even after that, they are going to decay to become more stable. So if you have way too many neutrons compared to protons, we are going to have a stabilization by emitting beta particles. So that is characteristic for too high neutron to proton ratio. Now, if we have too few neutrons or too many protons, those are going to be below this belt, and we are going to see stabilization by positron emission or electron capture. And if we have heavier nuclei, we are going to see a decay by alpha emission, which generally reduces the mass of the nuclei. All right, let's do a couple of sample problems. So let's predict the mode of decay for carbon-14. So from here we know, based on the atomic number, that carbon has 6 protons, and the number of neutrons can be calculated if we take the mass number, which is 14, minus the number of protons, so that is going to be 8. The neutron to proton ratio in this case becomes 8/6, which is 1.25. Now let's check where does carbon-14 ends up being on our figure. So because it has 6 protons, so it's going to be somewhere here, but with the 8 neutrons, it's going to be right above the belt of stability. So that means that we are going to have a high neutron to proton ratio, meaning that we have way too many neutrons, so we need to decay by emitting beta particles. So carbon-14 is going to get stabilized by emitting beta particles. All right, what about xenon-118? So in this case, we have a number of protons of 54 from the atomic number. The number of neutrons can be calculated using the mass number, which is 118, minus the atomic number. So that is going to give us 64 neutrons. So the neutron to proton ratio is going to be 64 divided by 54, which is 1.19. So we're still going to have more neutrons than protons. However, we have a significantly heavier element. So if we look at 54 protons, that is going to put xenon somewhere around here, right? So this means that in order to get a stable nucleus, we need approximately a neutron to proton ratio of 1.4 and around 70 to 80 neutrons, but we have significantly less, and the ratio is also smaller. So this means that the neutron to proton ratio is too low, so we have too many protons. So xenon is going to decay either by positron emission or electron capture. All right, I hope this makes sense. Now, interestingly, we have so-called magic numbers in case of nuclear stability. So more than half of the stable nuclei have even numbers of both neutrons and protons, and only a few stable nuclei have odd numbers of both neutrons and protons. Based on the Octet Rule, we know that atoms with 8 valence electrons are especially stable. Now, a similar situation applies to nuclei regarding the number of neutrons and protons that generate stable isotopes. And these are called magic numbers. As you can see, the numbers are here for protons and the numbers are shown here for neutrons. Now, these are all even numbers, 2, 8, 20, 28, 50, so on. And interestingly, in some cases, the isotopes can consist of magic numbers for both protons and neutrons. But these would be heavier nuclei because we will have a larger repulsion between the protons in case of heavier nuclei, and these are called double magic numbers. Interesting, right? Now, there are some radioactive nuclei that cannot stabilize by undergoing one nuclear transformation, meaning that they undergo one decay process, but the nucleus that is formed is still unstable. So we are going to end up having a series of decays until they form a stable nuclide. And quite often this is the nuclide of lead, just as it is shown in case of uranium-238. Using an alpha decay, we end up with thorium-234. Then with a beta decay, we end up with protactinium-234. Then it decays to uranium-234, and then it gets back to thorium, but in this case 230, and so on until it gets to a stable nuclide of lead-206. All right, I hope this makes sense. See you in the next video.